This video discusses our lifelong learning workshop paper, Unsupervised Progressive Learning in the STAM Architecture. We pose the unsupervised progressive learning problem, where agents learn dynamic representations and tasks from a stream of unlabeled data. What separates UPL from other work is no replay of previously seen data. We work in the streaming scenario with limited memory and compute time. Non-stationary input. The data distribution changes over time. This requires novelty and anomaly detection to identify shifts in the data distribution. Finally, the only memory is storage of compact representations and their associations with tasks, if given in the future. In UPL, we learn from a data stream in which the input distribution changes over time. As seen in the picture, we see an agent is gradually introduced to new types of objects in the data stream. The goal is to learn useful representations for some downstream task. We evaluate these representations periodically with unsupervised clustering tasks and supervised classification tasks using limited labeled data. As seen, we may evaluate over tasks consisting of recent object classes or the global tasks consisting of data seen from the start of the data stream. We differentiate our work from standard continual learning to emphasize that the representation learning in our paradigm contains no data labels, no task identifiers, either explicit or inferred, and no data replay. This is a realistic, challenging problem, such as monitoring a live video feed on an agent exploring changing environments. Popular, deep, unsupervised representation learning works require iterative training over unlabeled data and are not applicable to the streaming problem. While our method could be trained and evaluated with deep, unsupervised methods, the opposite is not true. To solve the UPL problem, we propose the self-taught associative memory, or STAM, architecture. Here, we visualize the high-level idea of STAM. Inputs are broken up into overlapping receptive fields and mapped to a bank of centroids, which are learned from the data stream in an online manner. The centroids are the key parameters learned by STAM. Here, we demonstrate our method over time. Centroids are updated in an online manner. Notice that over time this patch containing part of it too is updated. Short-term memory is limited in capacity and handles new novelty detections, visualized with new insertions by green stars. Centroids are moved from short-term memory to long-term memory if they are selected and updated frequently, as visualized by the blue arrows moving centroids from the short-term memory to long-term memory. Notice the number of centroids in long-term memory increases when a shift in the data distribution occurs, but remains roughly the same after it captures all important features. If performing a classification task, we use limited labeled data to associate class likelihood with patches matched to the labeled data. We consider a centroid to be class informative if the centroid is associated strongly with a particular class or classes. This is visualized in the legend in the bottom right. Given a query image, each layer votes for a class based on aggregated patch-wise votes over all receptive fields. We only consider votes from class-informative centroids. In our experiments, we evaluate the representations with small clustering and classification tasks. The data provided for these tasks is not part of the agent's learning and does not affect the model's parameters. Rather, it is used to evaluate how well the learned features are. We specifically provide a small amount of labeled data from all classes seen at any point in the data stream and then perform a classification task. We use the same protocol for the clustering task but do not provide any data labels. For our experiments, we perform classification with limited labeled data and clustering accuracy with unlabeled data. There are no other works designed for UPL. However, we show a few intuitive baselines to compare with STAM. RotationNet, a self-supervised learning method, convolutional autoencoder, and principal component analysis. We show both tasks for the MNIST dataset of hand-drawn digits and SVHN dataset of street view house numbers. Notice that STAM performs strongest in 3 out of 4 experiments. For future work, we plan to experiment with more complex datasets, design new tasks for UPL, design new stream scenarios for UPL, and create new deep learning-based models for UPL. Thank you for watching our video.